record it. We're going to start to introduce ABO trees in chapter 26. In the preceding chapter, chapter 25, we introduced binary search trees. On average, binary search tree is well balanced. So the height is in order of log n. If you have n elements, so the height it's order of log n. When you perform search, it's taking order of log n time. For insertion and deletion, or takes order of log n time. It's very efficient. So this is data structure. It's a very elegant data structure, and you use it's a linked structure. So when we implement linked list, we use the linked structure, and that's you have the links and go to next. That's one-way linked list. You can have two ways, and you have next and also previous. So that's for one node. You have this contain the element, and then you have the links, the linked structure. And here in the binary search tree, and we also use linked structure. And it's this linked structure. We have a node, and the node has this two links going to the left and right. So this is something we're going to use it in the data structure. When you create your custom data structure, you can use it. So that's what we're doing here in the binary search tree. We have this the linked structure left and right. Now with binary search tree, it's very nice. You have this property. It's very efficient for search, insertion, and deletion. But in the extreme situation, you could end up with everything on one line. So that becomes order of n time for search, insertion, and deletion. And now we're going to have another kind of binary search tree. This is called ABO tree. So this tree will guarantee that we have the height is always balanced in any case. So it's going to be order of log n time for all the operations in any case. All right, so now let's look at this tree. So this ABO tree, it's called an ABO tree because it was invented by two people with their the name initial. So this is the name. It's ABL. It comes from this two people, and it's Anderson Velsky, so AV, and then Landis. So this is L. So this is using their names initial, and this is so-called ABO tree. For this tree, ABO tree, there's one property is that we're going to define this the balance factor. So the balance of factor is this. It is the so it is the height. So for any node, we're going to have a balance factor. So any node we have the balance factor is the height of its right subtree minus the height of its left subtree. So the difference between the heights of its right and the left. So this is the right, the height of the right subtree minus the height of the left subtree. All right, so look at this 60 here. So what's the height here? You're going to see this is one more than on the left. So this is 1. And this is 107. So that's nothing here. And this is 0. The height is 0. And this 67, the height is 1. So it's here. And this is for 55, the height negative 1, because here it's on the left is one more than the height than the right. All right, so this is here, and you can look at and other examples. You can do it and on your own, see what is the height for this tree. If this is tree, what is the balance factor for each node? So the balance factor for each node is here. All right, the balance factor is it if the balance factor is 0, 1, or -1. So this node is called balanced. So this is balanced. Every node is balanced in this tree. So the entire tree is balanced. And this entire tree is called an AVL tree. All right, so this AVL tree is a subtype of the binary search tree. So you perform the search in the same way. So this is the everything for each node. And so everything that's left is less than this node, and on the right is greater than this node. So that's the search property. We have this, we can perform a search. All right, so I'm gonna go to look at this animation. So we're gonna use this animation when we introduce all the algorithms for this AVL tree. So first, search is the same as before. So we're gonna do a search for 35. So now you're gonna see this is 35 is less than 50, and 35 is greater than 25, and here is a match. 35 is here. Okay. So if you do a 47, so here is search for 47. 47 is less than 50, and 47 is greater than 25, and then 47 is greater than 35, and so it's not there. So, and 47 is not in the tree. There's nothing after this 35 on the right. There's nothing. All right, so that's a search just the same as in the binary search tree. So this is the AVL tree itself. This is AVL tree. Now, look, this is AVL tree. Look at every node. What's the balance factor for 50? It's -1. So because this is on the left, the height is one more than on the right. So, all right, let's insert 37. So see what happens. So we're going to insert 47. So 47 is greater than 25. So it's going to go this side. Okay, now we're going to insert 47 here, but you're going to see there's an issue here. It's not a balanced. Do you see this is the 47 will be inserted here? So what will be the balance factor for 47 itself is 0. For 35 now, what is balance factor? It's going to be 1. And for 25, the balance factor is going to be 2. So that's not balanced. So we need to perform operation to make it balanced. So the operation we're going to perform, it's called rotation. So in this case, there are 4 rotations I'm going to introduce to you. So this rotation here is called RR rotation. It's a right rotation because it's heavy on the right. So we're going to perform the rotation at 25. So after the rotation, so everything is now balanced. All right, and now I'm going to get into the next one. I'm going to open another tab. So I'm going to open another tab here. All right, so this here, open this tab, and let's get into this tree here. It's right here. We're gonna see how we're gonna do the rebalance the tree. All right, so when you insert into the tree, before you insert it, it's fine. But after you insert it, it may cause something not balanced, right? All right, so if it's not balanced, how are we going to do it? We're going to perform the operation called rotation to rotate it, to make it balanced. All right, and you can see this is all the cases here. And the first case is this. So we have this guy here, this note is the first one is going to be unbalanced. This is the -2 means it's left heavy, right? It's heavy on the left. There's more depth on the left. All right, so for the child of this A, it's B. B is potentially heavy on the left. So it's at least maybe equal to the right side, but it could be potentially heavy on this side, on the left side. All right, you're gonna see this is this case, we call this is LL. It's left. It's heavy on the left. All right, the way we're gonna perform the rotation is you can see visually, you're gonna turn around. So what you're gonna have, it's B now is here, it rotated to the right, and so here is, it's like this. So, and B is becoming the position for A, and A is now becoming a child, the right child of B. So this T2 previously was the right subtree, now becomes the left subtree of A. So now with this operation, everything is now back to normal. It's going to be balanced. These two nodes are balanced. All the others, we didn't touch any of this internally, all these nodes in this T1, T2, T3. So only these two, now you look at these two, and they're balanced. So the entire tree is now becoming balanced. So that's AOL. All right, so another case, this one is called RR. It's just opposite of LL. It's everything is heavy on the right. So here is this A is +2. So here the right subtree of A is 2 more than this left subtree of A. So here is right here. And further, this B is a child of A, and B is the balance factor is either +1 or 0. So this is potentially it's right heavy. All right, so what we do, we turn around to the left. So that's, and this is how we do it. All right, so we make this and a B as the position for A. So A now becomes a left child of B. So look at this T2 was the left subtree of B now becomes a right subtree of A. This is called RR rotation. And now there's next one is called the LR rotation. Is here we identify this A, and the balance factor is -2. So that is heavy on the left side. So on the left side, and the height is 2 more than on the right side for this A. And here B is the balance factor is +1. So this one here on this side, on the right side of B, it's heavier than the left side. So what we're going to do is to do some rotation. So involving this A, B, C here. So here's a C right here. This is C right here. So involving the 3 nodes and do this rotation. So you can see this, the result of rotation is C becomes in the position of A, and B now is here as a left child of C, and this A is becoming a right child of C. So then accordingly, we can put this T3 as the left subtree of A. All right, so this is the LR rotation. And to fix this situation, it's imbalanced. We call this is LR imbalanced. It's LR imbalanced, so we're going to perform LR rotation. All right, similarly, it's just the opposite. It's the RL rotation. It's right heavy, and then B is the left heavy. So L it's RL rotation. All right, so now you can see all this rotation. And for this, I'm going to look at this animation right here. So here in this animation, let's do this here. I'm going to have this. Okay, I'm going to add. Let's say we're going to add 40. So let's add a 40. So what happens if you insert 40? Okay. Okay. All right, which one is now unbalanced? Which node is going to be imbalanced? It's going to be 50. And what's going to perform? It's LR. Why it's LR? It's left heavy, right? For this 50. So all this, look at the balance factor. Only 50 is the one, it's a -2. So this one, 35 is +1. The balance factor for 35, +1. For this, 47 is -1. So this balance factor is 80 is 0 and 25 is 0. So this is 50 is the only one. So if you go all the way up here and you perform this along the path, so you add 40 and it go up. So that's the one here along the nodes along this path may change their balance factor. All the other nodes, they're not going to be affected. So this here, we're going to perform LR rotation. So LR rotation here, it's at 50 and it's left heavy, and here going to right LR. So now 47 will be in the place of 50, and 50 will become a right child of 47. All right, so this here, you're going to see this here, 37 will become a left child of 47. So this is what happens. That's the rotation it's performed. Okay, so let's do another one here. I'm going to add, let's add 60. So I'm going to add a 60. Okay, look at this. 60 is going to be placed right here, 60. Okay, as the left child of 80. 60 is going to be placed right here. So if you go along the chain from this 60, go up, which one will be unbalanced? The first one is discovered. Which one will be unbalanced? And that's going to be 50. So what will be the balance factor for 50? It's going to be 2. All right, 2. So here it's right heavy, and then this going to the left, it's RL rotation at 50. So if you do this insertion, now you're going to see that. All right, see, it's RL rotation at node 50. Okay, so when you do this rotation here, so 60 will be in the place of 50, and 50 will be the left child of 60, and 80 will be the right child of 60. So that's it. All right, so that is here. It's all this, the rotations. All right, so next, I'm going to open another tab. All right, so let's look at the next thing we do is we're going to design this class for ABL tree. So we designed the ABL tree as a subtype of the BST. So now look at this ABL tree is a subtype of BST. For the ABL tree, we're going to have this ABL tree node the area tree node, we need to add one more thing, is the height. For each node, we need to have the height. And with the height, we will be able to compute the balance factor. So, and this area tree node is subtype of tree node. All right. So this area tree here, you can see this is all the constructors, and this is the we're gonna do override, create new node here. It's gonna be area tree node. Insert and delete. Now search is going to be inherited from BST. We're not doing anything with the search, but we have to modify the insert, because after you insert something, and you have to check if it's still balanced the entire tree. If it's not, we're going to perform the appropriate rotation. All right, so here we have the other things. So the other private methods, update height and get a path. And so to identify, and the in order to identify the nodes that is imbalanced. So so here's the balance factor, and this is the performing the balance rotation. So LL rotation, and LR rotation, RR rotation, and RL rotation. Okay, so here, this is the area tree node. It actually has left-right element, just like you have from the BST. So it's now additional thing is the height is here. All right, so this is the diagram for area tree. All right, let's open the next tab. All right, so the next section, we're gonna see how we're gonna implement the insert method. So the insert method is already in the BST. Now in the area tree, we're gonna override it. We're gonna override the insert method. So we're gonna override it, and all right. So this is how we're gonna perform when you override it. You need to do this. You need to find this is the new node you added. So here's the diagram. You need to go along this path all the way to the root. So let's find the first one. Suppose this is the A, it's not balanced. Okay. So if everything is balanced, we don't do anything. So, but we find something here, it's not balanced, like here is A. So the parent of A is here. All right, so here, and now we're going to perform the balance. We're going to balance this is called a balance factor, we balance path. So this is how we're going to do this, identify. So here we get a path from the node that contains the element. So this is the one, the node all the way to the root. So that's the path. And then for each node A in the path leading to the root, we're going to update the height. So we're going to update the height. All right. And update the height. And then we're going to look at this, the balance factor for A. So if it's not balanced, in any of these two cases, we're going to perform the balance, rebalance it. Otherwise, we don't do anything. So that's how you see this is how this works. All right, so now we're going to do this. This is to, if it's not balanced, look at the two cases, -2 or +2. If it's -2, it's left heavy. And so we're going to further look at A dot left. If it's further, it's left heavy, and then we're going to perform L. But if this is right heavy, so left heavy, right heavy, it's performing LR rotation. All right, so this is how you're going to override the insert method and performing this balance path. I think I'm going to jump to the implementation. You're going to see the code for this. So let's go to the implementation. I want to open another tab. So let's do this. Maybe keep this tab here and open another one. Okay, right here, I have this this class here. We're going to implement this class now. I have all the source code. So I got all the source code here. Let's look at insert. So do you see this? Where is we write the code right here, insert. Okay, do you see the insert here? Insert. So this insert right here, insert. Okay, so what you do with insert? Okay, so here you're going to do a super insert E. Okay, so to invoke the superclass insert, the superclass is this right here, AVL tree extends BST. So here, if it's not as successful, means E is already in the tree. So what you're going to do if it's not successful? Okay. Well, you don't do anything here, just return false. Okay. So return false. Okay. All right. So else we're going to do this. It's to make sure is going to be balanced. So it's to invoke this method here. It's balanced path. This one here, we have the one before. So this one balanced path E. So it's balanced path E. Okay. All right. So now what you do with this, you always return true now. Okay. So you insert it, successful. All right. So this is the balance path. The algorithm we just look at it right here. This is the algorithm for this balance path. All right. And this is the code for balance path. The code is here. And the code is right here. It's right here, balance path, right here, balance path. And just see how it's implemented right here, how you write the algorithm and now how you're going to write the real code. So everything is here. You're going to see this is to see the implementation. All right, there is one thing here, this one here. So what we did is the balance factor here is switch. So here's balance factor of this A. So we look at this A. If it's -2, so we can look at further, there's two cases. If it's +2, there are also two cases here. All right, this is the balance factor. How do you compute a balance factor? So this is the balance factor, how we're going to compute it. Okay. All right, just do it quickly. I'm just not writing anything. Just go down here and you can see how we do this, all this code here. So how we implement this, all this code. So what is the balance factor? What's the node? If the node dot right is null, so the balance factor is node dot height, and it's a negative of node dot height. So okay. All right. I think what you need to be careful is with the definition of the height. So what is the definition of the height? It has very strict definition for the height in the binary search tree. The height is this. If the tree has only one node, the height is 0. So if the tree is empty, the height is -1. So that's the definition. All right. So that if the tree has this 2 nodes, let's say you have a root and the left child. So what is the height of the root? It's just 1. And what is the balance factor? It's -1. Okay. All right. So the next thing here, we're going to look at the implementing or rotation. So here we have look at the code for this rotation, how you implement this rotation. There's a code here. So this is the algorithm. So let me just also get the algorithm with another tab here for the algorithm. All right, so here's implementing rotation. So how you implement this? Balance LL and this rotation, how you're gonna implement it. So you can compare this and open another, I think it's probably the best, maybe just look at this. When you study it and you're going to look at this diagram. So here is LL. So look at this diagram and also look at the algorithm. And now you're going to see how you do this. So when we solve a problem and we have some ideas, and it's really nice when you have these ideas using a diagram to illustrate your idea. So this is a diagram to illustrate the idea. But you need to write the algorithm for this idea. So here is the algorithm for the idea. So this is the algorithm, balance LL, this is the rotation. And then finally, and you're going to write the code. So this algorithm is language independent. When you finally implement it, it's language dependent, depends on the language. Okay, we're gonna finish this chapter in the next lecture. And I think I'm gonna stop here and let you read it and digest all this material. This is a very nice, elegant data structure. You're gonna appreciate really the beauty of this data structure and the underlying algorithm. And so this is the purpose for this chapter. Any questions? All right, so let's meet for the next class, and we're going to finish this the rest of this chapter. Goodbye. Anybody has questions? I'm going to stop recording.